Okay, so in this video now I want to talk about how to determine the number of unique proton NMR signals that you would theoretically predict given a compound. We'll start with this example here. So because of the internal plane of symmetry, that is going to cut down on the number of protons in this compound. The alcohol protons are identical. They're both on the same atom. They're 1,3 to each other. They're cis to each other. And we can see they're the same because they reflect one another across that internal plane of symmetry. Likewise, the protons that are alpha to the alcohol are equivalent. Okay, turns out those are enantiotopic, but you can fold the compounds and these would superimpose. However, the protons that lie along this plane of symmetry are not the same. This one is cis to both alcohols, while its partner is trans to the alcohols. So those two protons are on the same carbon, but they are they're structurally equivalent, but they are stereochemically inequivalent. So they are diastereotopic, and they would show up at different chemical shifts. Another unique set of protons is this enantiotopic pair that mirror one another across, the plane of symmetry. They are each cis to the alcohols, I think it's pretty easy to see why they are equivalent because of symmetry, but they are not equivalent to the proton on the back. Once again, the brown one, is trans to the alcohols. The red one is cis, and so those two protons are diastereotopic. So here we would predict an overall proton count of 6 unique protons. So you would expect 6 unique NMR signals in addition to your solvent or standard. Another example is this trans 1,2 diol. Although there's not as much, there's not a clear internal plane of symmetry in this compound, it's not meso, there is an axis that we can rotate about. And if we rotate about that axis, this hydroxyl that is coming forward will rotate 180 to become hydroxyl back. So you can flip it around and cause this hydrogen to interchange with the other hydrogen. Those alcohols are chemically equivalent because there's nothing on the front face that distinguishes the wedge from the dash. The two faces of the molecule look the same. Likewise, this purple proton back would interchange with the purple proton forward. Those protons are equivalent. Simply upon rotation about this axis, 180. This proton here is cis to its neighboring alcohol and would rotate 180 to become a dash backwards where it is cis to its neighboring alcohol. That's another set. The final unique proton set I'm showing here in green is trans to its neighboring alcohol. And that relationship holds here. So overall, I get 4 unique protons for this compound. For the next one, this chlorine does not really have any stereochemistry that's relevant for the compound, but it is certainly not planar, as we've shown here with this straight line. It is on an sp3 carbon, and therefore it is tetrahedral in geometry at the sp3 carbon. Either the chlorine is a wedge or a dash, always, right? It's always either on top of the ring or underneath the ring. It's not coplanar with the ring. So I'm just going to bold the chlorine to show that it's always on one face. Doesn't matter which face. And that will emphasize that one face has a chlorine and the other face of the ring has a hydrogen. So that distinguishes the two faces of the compound from one another. In other words, this proton that is adjacent to chlorine is one away in cis, while its neighboring proton of the methylene is one away from chlorine, but trans. So those are diastereotopic. Because of symmetry, the red proton is duplicated on the other side. They're enantiotopic, as is the green one. Okay, red is 1,2 cis to chlorine, green is 1,2 trans. Finally, this position is unique structurally because this is 1, 2, the 3 position. And that 3 position has 2 protons on it. One is going forward, and the other goes back into the page. Okay, once again, one is cis to chlorine, and the other is trans. So those are diastereotopic. So here we have an overall total of 5 proton types. Let's go next to this alpha beta dienone. So the methyl group here is unique. It's the only one of its type. This proton is cis to the ketone and cannot rotate to interchange with the green one, which is trans to the ketone. So because those are on a double bond, right, this bond has hindered rotation, they are diastereotopic to one another. And they cannot interconvert. So next, this proton is the only one of its type. And the protons at the end of this vinyl group are also diastereotopic, because this one is cis to the ketone and the other is trans to the ketone. So protons at terminal vinyl groups are often diastereotopic. So here we get an overall total of 6 signals. Finally, here we have a unique methyl group that's one away from a nitrile. This proton is unique in that it shares a carbon with nitrile. This proton is unique in that it's only one of its type on that tertiary carbon. However, these ethyl groups have some similarity. The ethyl groups, you can rotate about the carbon-carbon single bond to interconvert them. And in fact, if you do R&S, you will find that the proton that is a wedge here would interconvert and become a dash there. Those are chemically equivalent. Next, the proton that's a dash on that methylene is a wedge here. And finally, the unique methyl group at the end is the last signal. So I get a total of, let's see, 1, 2, 3, 4, 5, 6 unique protons here. If you did the isotope replacement test, you would find that these protons here are diastereotopic. The reason they are diastereotopic is because you have a fixed chiral center with configuration S. So every CH2 is a diastereotopic set, okay, if you have one chiral center in the molecule. So with that, you can find more practice on predicting numbers of protons and topicity in the Unit 1 of my Orgo 2 course guide at chemguides.com.